Hello everyone, this is the video lecture for Calculus 3, section 15.9, Jacobians. So let's talk about Jacobians. Jacobians are a capital J, and it's equal to the determinant of del x, del u, del x, del v, del y, del u, and del y, del v. So the partial derivatives of x and y in respect to u and v in this determinant form, which if you've done determinants in a while, you cross multiply and subtract those. So just as a quick simple one, it's x sub u times y sub v minus x sub v times y sub u. So that's the quick, I guess, like Newtonian version versus the Leibniz kind of version there. How Jacobians work is basically we have a double integral over some kind of region of f of x y dy dx. It's dA technically, but dy dx is probably more accurate in this particular point. So I have an integral. I can rewrite that integral as f of, and this is going to be g of uv, comma, h of uv, and then times j, that thing up there, times du dv. Now, I think this is a bit technical. I don't like the technicality so much because, honestly, this right here is x, and this right here is y. It's just x in terms of u and v. It's y in terms of u and v, okay? So basically, you had a lot of x's and y's to start with. Now you got a lot of u's and v's. You throw on a j, and it works. So there you go. What's the purpose of this? I'll get to that in a minute. So let's actually do some simple Jacobians. And we'll build up from there. 15,9,011. I got x is equal to 6u plus v, and y is equal to 7u minus v. And they say, what's the Jacobian? So, sorry about that. If you keep in mind, I'm doing my x sub u, so derivative in terms of u is a 6. Derivative in terms of y in terms of v is a -1, minus sign. And then my derivatives of the other ones. So x in terms of v is a 1, and then y in terms of u is a 7. So we basically got -6 minus 7 makes a -13. Pretty easy. Next one. 15,9,012, I have x is equal to u squared plus uv. Make that a little bit better looking, uv. And I got a y, which is equal to 6uv squared. So what's my Jacobian going to be? X in terms of u is 2u plus v, if you take your derivative there. And then y in terms of v is going to be a 12uv minus. Now, x in terms of v is just a plain old u, and then y in terms of u is a 6v squared. You could, of course, distribute and simplify and stuff like that. It takes a minute. So I got 24u squared v plus 6uv squared. So there's my final answer after simplifying. So now that we've got that done, y Jacobians. Why even do Jacobians? What's the point of all this, etc.? Well, a very common thing that happens is that you have this shape, this region here, that kind of maybe looks like this. So this right here is your region R, and it's for x and y. If you wanted to integrate this, even if you wanted to find the area, it's not so easy because, honestly, you're going to have to do integrals like 3 or 4 different kinds, and you're going to have to break them up. Notice that you have a top and a bottom, a top and a bottom, a top and a bottom. That's 3 different integrals, a whole lot of different collision courses, all kinds of different lines. Is it possible? Yes. Is it fruitful? No. And so what Jacobians do is it converts it into a UV basis where that parallelogram of some kind actually probably ends up just being a plain old rectangle over here. I can't remember what they use. I think it's an S maybe, but basically we're changing our region over into U's and V's, and that's it. Look at how easy that integral is. I don't know. Let's just say it ended up from 0 to 5, and then from 0 to like 10. Well, then your double integral here is 0 to 5, 0 to 10. I mean, we are talking easy math now, right? This is great. We like that. Versus here, you would have an integral, a double integral. Actually, I think it would be a single integral. Well, single or double, plus another one, plus another one. It's just not worth it, man. So that's why we do Jacobians. Do you always need Jacobians? No. Obviously, we've gone through all of Chapter 15 without them. But in some special cases, they are important. So it's just a tool that you rarely use, but it is a tool that's helpful when you need it. So we got now double integral over region 12x plus 8y dA. They say that this is actually going to be for a parallelogram, kind of probably something like I just did there. They give me some points, -1, 3, 1, -3, 4, 0, 2, 6. Okay. They also give me x and y in terms of u and v. This is very helpful. It's very nice whenever they give you these sort of things. They will not always give you those. So sometimes they'll just leave off. And we have to find them for ourselves, which is not terrible. A lot of times it's kind of obvious, but at least now they're here. That's easy. We like that. Okay, what I want to do to actually make this look real, to make this come alive for you, I'm going to graph this parallelogram and see if you like to do a double integral for it, okay? So -1, 3, 1, -3. We got 4, 0, and then we got 2, 6. Okay. There's my region. There you go. Do you want to integrate that? Single integral, double integral, anything like that? Look, you're going to have a top and a bottom, all kind of things. You actually have a line right here and a line right here. So you'd honestly have 3 different integrals just to kind of figure out what's going on. That is not fun. Not fun. So let's not go there. We want to convert this into something more basic, okay? So this was xy. My goal is to make this into a UV of some kind that I like. And I will show you what that is, just not right now, because I can't honestly tell you what it's going to look like. I can't just give you the answer by looking at it. I've got to do some math to get there. And once I have it, though, it's going to be super easy. So what I want to do is I want to first off find the Jacobian, because we have all this x's and y's. Let's go ahead and solve for it. X in terms of u is going to be a 1/4. Y in terms of v is going to be a 1/4. X in terms of v is a 1/4. And then y in terms of u is a -3/4. Notice here that we have 2 negatives will make a positive. So we got 1/16 plus 3/16. 4/16 is 1/4. So this is good. We like that. That's an easy number. We're just going to throw it in our integral, and amazingly, it'll work. Okay, now my goal, here I'm gonna state my goal here right quick. My goal is to find out what my graph looks like in the UV dimensions. So again, I know what XY looks like. I know this, but what is this going to look like? And if I know, like, I'm going to tell you ahead of time, it's going to look something kind of like that. So if I know what it looks like, I can then take my limits, you know, left side, right side, bottom, top, double integral done. So how do I get to that shape? How do I know what it's going to look like? Okay. So what I'm going to do is I'm going to do it the long way with you, and then if you want to do a shortcut method later, that's fine. I just want to make sure you see the process in full. Okay. So my X and my Y, let me rewrite them. There we go. Okay, I want to start solving. My goal is actually U equals something and V equals something. So that's my goal. Let's see if I can make that happen. This 4 right here, I'm going to toss it to the other side. Same over here. Well, let's work on this guy here in a minute. We're not there yet. So 4x is equal to U plus V. And then I need to get, like, let's say u by itself, so minus v on both sides. So u is equal to 4x minus v. Let me pause the recording for 1 second. All right, so now that we got u equals 4x minus v, let me take that u, and I'm going to plug it in over here. Now, before I do that, I do want to move that over. So I got 4y is equal to v minus 3 times 4x minus v. Let's solve for v somehow. So first off, distribute your negative 3. So 4y is equal to v minus 12x plus 3v. These v's are going to combine, but I want to move this guy over. Let's move over my x. So I actually have 4v is equal to 12x, positive now, plus 4y. Of course, divide by 4, and so my v should be equal to 3x plus y straight up. This is really awesome. We like that. I'm going to take this and basically plug it back into this one to find my u, completely with x's and y's. Oops, that's just a y. Distribute and combine, so you got 4x minus 3x is going to be a 1x, and then minus the y. So I got my u, and I got my v in terms of x and y. Let me just rewrite them so that they're set in stone, essentially. Okay, so these are my equations that I'll be using to find what points I need in my new plane. So I'm going to go through each xy point, and I'm going to plug them into this to see what uv equivalent is. So let's start. I have my points up here as negative 1, 3. So I got a negative 1, 3. And I'm going to plug that in to see what my u and v are. So u would be then negative 1 minus 3. It's a negative 4. My v at the same time would be negative 3 plus 3 is 0. So I actually end up with a uv point at negative 4, 0. Okay, let's do it for another one. Let's do it for 4, 0. And I want to find, again, my uv equivalent there. So my u would then be 4 minus 0 is a 4, and v is equal to, when I plug that in, I got a 12, plus 0 is 12. So then my point should be 4, 12. And you can do the other two this way, and you will find those other endpoints. But I'm telling you, there's something about having these right here, okay? What's going to happen is, basically, there's two of them that are further apart from one another, and they'll basically describe your rectangle easier than having to go through every single point. Could I go through the other two and find out what they're going to be? Yeah. I'm just imagining that I'm probably going to get positive 4, 0, and then I'm also going to get a negative 4, 12. How do I know that? Well, it's just because I've been doing it a while. I just know that I'm going to have a rectangle, and these are opposing corners, essentially. So, again, watch out for some tricks like that you can use to help speed up the process. So where is this going to end up being? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's good enough. So basically it's a rectangle that looks kind of like, well, close enough, kind of like that. And there's my new region. This is much easier to integrate. So when I'm going to integrate blah, 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 du, dv, my u's are going to go from negative 4 to 4, and my v's are going from 0 to 12. So much easier than having 3 separate integrals and all of them being a mess. This is a very good thing, okay? So that's what my uv equivalent would be. All right, now we've set it all up. We've basically got my Jacobian, which was 1/4. I've got my regions, the negative 4 to 4 to 0 to 12. Everything's fine. I even figured out this u's and v's thing, which honestly I don't think you're going to use anymore. But you could at least always go back to this x and y business right there. So let me take all the stuff and put it all together, okay? My original that they wanted was double integral of 12x plus 8y dA, right? And what I'm going to do is say double integral, now, negative 4 to 4, 0 to 12, this is my UV stuff. I'm going to replace my letters here. So I got 12 times, and what was x? x is equal to 1/4 of u plus v. Now, please don't get my 4's and u's mixed up. I'm sorry, my handwriting looks like that. And then plus 8 times my y is 1/4 v minus 3u. Sorry, they switched it on me. Okay. 12 times, there's another parentheses there, there's one here, there's another one there. J for my Jacobian was a 1/4, and then finally du dv. That's my J right there I'm putting in. Okay, wow, what is going on here? Well, honestly, a lot of this will simplify. Notice that we got 12 over 4 is going to make a 3, and the 3 you can distribute. Here we got 8 over 4 is a 2, 2 is going to distribute. So we got double integral of 3u plus 3v plus 2v, and then minus 6u, all this times 1/4 here in just a minute, du dv. These guys here will combine. Those will combine right there. So then what I have then is a negative 3u and a positive 5v, 1/4 du dv. Okay, cool. My goal now is to actually integrate this. This is negative 4 to 4. This is 0 to 12. Super easy to integrate at this point. So integrating in terms of u, because that's what comes first, I'll have a negative 3u squared over 2 plus 5 uv from negative 4 to 4. I guess I forgot my 1/4. Let me go and just toss that in the front so everyone's happy. There we go. So we won't forget it now. Go ahead and plug in the 4 and the negative 4, all that kind of stuff. It's kind of funny. Whenever you plug in a 4 into this, you're going to get a negative number, right? But minus a negative will make a positive. But when you plug this in, it's not going to change the sign. Therefore, this actually cancels out, given that they're equivalent numbers, but in different signs. Kind of strange how that happens sometimes. You can still plug them in here and actually get values, of course. So plugging in the 4, you would get a 20v minus, and then you plug this in here to get another negative 20v. And so what happens is two negatives make a positive, obviously. 1/4 integral of 40v dv. The 40 can come out to the front to make that 4 and 20 a 10. I'm sorry, the 4 and 4 a 10. 0 to 12 v dv. So then v squared over 2, of course, 0 to 12. The 0 is going to cancel. 12 pops in to make a 144. 10 times 144 all over to 2. My answer is 720. Whew. We just did that. That was your first big Jacobian. Let's do another. So I got 15.9.1019. So I've got double integral over a region of 7x squared dA. Cool. They say that my region is bounded by an ellipse, and they give me the ellipse is 4x squared plus 9y squared is equal to 36. They also say that x is equal to 3u and y is equal to 2v. Okay. I'm happy when they give those to me. I don't have to go and search for them. We will have to search for them eventually. I know that I'm going to be doing Jacobians just because that's, the section here. So what I want to do first off is convert this into my UV kind of region, I guess. Right now, we're having an ellipse. When you divide everything by the 36, I'm thinking that your x's are going to be the majors, and so it'll look something kind of like that. The problem is that it's not that bad unless you need to go and do like, 36 minus 4x squared all divided by 9, and then it kind of gets it's, I think by 3. But it's going to be a mess trying to get all this stuff to work, and there's a plus and minus to that. That's terrible to integrate. Don't do that. Wouldn't you rather do polar form for something like this? Doesn't that look like polar form would be better? Well, yeah, the problem is that polar form doesn't do ellipses as easily. I mean, it's possible. It's just not as fun as a circle. So my hope is that this will turn into a circle. It's very close. So let's try. I'm going to take these and literally plug these in, And we're going to see what happens when I do that. So I got a 3u and then all squared, and then I got a 2v and then all squared. And I messed this problem up really, really badly the first time I did it, because I forgot to square the whole thing on the inside. I simply said 12u squared. That is incorrect. That is incorrect. That is 9u squared now. And here this is 4v squared on the inside. And so when you actually multiply 9 and 4 together, you're going to get 36, 36, and 36. Of course, you cancel those. And that is so much nicer. Look, that's a unit circle. Basically, you're now going to integrate a unit circle, and hopefully in polar form, and then you're done. Super, super easy. One last thing before we jump off the deep end, my Jacobian. So x in terms of u is a 3, y in terms of v is a 2, and then they don't have the other terms even in them, so they're zeros. And so we got 6. Jacobian 6, we got our new region. Here we go. It's double integral of 7x squared dA. I'm going to convert into, let's just go ahead and do the uv thing. I'll do the polar here in just a few minutes. So 7, my x, if you go up and plug it in, turns out to be a 3u, all that squared, Jacobian of 6, and then du dv. I mean, that's all we're doing right now. I didn't do polar yet. I'm going to do polar in a minute. That's my goal. But I'm looking at this thing, and I'm saying, okay, well, let's just see if I can integrate this. Well, if you distribute your square, you'll get a 9 there, right? So 7 times 9 times 6. 7 times 9 times 6. We get a big number, 378. 378. So what we're really doing is 378 double integral of u squared du dv. That's honestly what we're really going for. But remember, our region is the unit circle, right? So what I'm trying to get at is, I don't think that this would be easy by putting a lot of square roots all over the place. That's not cool. Instead, let's try polar. So I'm going to go polar. And so instead, I will see this as like a radius of 1 and all that stuff. 378, double integral. And then so my u is kind of like an x in a way. Like, I don't want to go too deep into this, but remember how we got x equals r cosine theta and y equals r sine theta and all that stuff. This is for polar mode and stuff. I'm kind of like replacing them with u's and v's right now because I already used x's and y's. So let's not get confused. I'm just going to redo it like this. So u is going to be equal to r cosine theta. And you can see I have it squared. So that'll be r cosine theta all squared. And then my I already have my Jacobian. So I'm converting this into polar. I need my requisite r, dr, d theta. Okay, my requisite r, dr, d theta. Now, if I wanted my limits for this, is actually very simple. My r goes from 0 to 1, unit circle, and then I go full circle, 0 to 2 pi. Super easy. So let's keep going with that. 378. I'm going to go ahead and distribute my square. So you got a square plus another one makes a cube, and so when I integrate, it's going to be a 4th over 4 cosine theta from 0 to 1 d theta. Plug in the 1, obviously you get a 1/4. You can just toss out in the front there. I'm sure it'll cancel to some degree. Oh, that's a cosine. I don't know what I was thinking there, sorry. It's already integrating. There we go. So I'm integrating my cosine to make that sine. And again, from 0 to 2 pi. Actually, no, I forgot something. Hold on. Right here. I'm sorry. Forget what I just did a second ago. Let me erase all that. Notice here, I had it squared, but I forgot to square it right here. So that's my bad. I definitely messed up there. This is a square. This is a much different integral now. Honestly, you know what I did? I'm looking at my notes and I see what I did. I did this in the calculator because it's actually pretty basic. So if you wanted to go and do that from the formula book, that's fine as well. But just as a quick note, right quick, TI-83, 84s and all that stuff will work with that for sure. It's just I'm just doing it really quickly. It comes out to be a pi. So wow, that was easy. So in the end, it's 189 pi over 2 because these guys cancel just a tiny bit. There you go. Not too bad in the end. All right. I have one last question. This one here is where we have to find our x's and y's. So this is a pretty big problem here. And I kind of messed up on this problem myself. And then I had to go back and discover what it was. I had done something too late instead of too early. So I'll show you what I mean here in just a second. 7 times, and I got x minus 3y all over 4x minus y dA. Okay. And they say this is a parallelogram, and they give me x minus 3y equals 0, 4x minus y equals 7. I got x minus 3y equals 1, and then I got 4x minus y equals 8. Now, this is a blessing in disguise. What's going on then is they don't actually say that x equals something or other and y equals something or other. We need these in order to actually find what my Jacobian is going to be, because I need to partial derivatives and all that kind of stuff. But they're not giving it to me. What they are, though, they are giving it to you in a format. If you had to pick a u that looked kind of like the previous u's we worked with, oh, I don't know, let's just go ahead, I don't know, let's just pick the numerator. If I had to pick a v, oh, let's just choose the denominator. That sounds fine. So I got my numerator, I got my denominator. And if this is something I'm picking, this is my choice, notice that my domains for my u's and v's are pretty simple. This is a u, this is a u. So I'm saying that my u's are going from 0 to 1. My v's are going from 7 to 8. So, like, I'm already now creating my double integral limits. And then all that stuff after it. Du, dv. Cool, huh? So, if they don't provide, just go ahead and look around for something that looks really common. And, well, indeed, that looks very common. So, no problem there. Get rid of those because they looked a little kind of confusing to me. Okay, cool. All right, then. So now that we have this all set up in that regard, let's go and actually get my integral to work here. So I'm going to say now double integral 7 of u over v. Again, I need my Jacobian, and then du dv. My problem, what I messed up on, was that I didn't find j right now. I went all the way down, and then I found j at the very end and tossed it in. You need to find j as soon as possible, not because it's required to always be that way. I still got the right answer. I'm saying that j might have variables. A lot of times, and what you see here is that j is just a number, right? What was the last one? Was 6. And the one before that was just a fourth, right? He was just a fourth sitting out in the front. You can't always do that, because on our second problem, if you go way, way back here, way, 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 way back, our second problem, look how j actually was a formula with u's and v's. This sort of thing does happen sometimes, so what you really need to do is find j first, plug that in, and then you can go ahead and start doing your integrals, okay? So it's very important to get j as soon as you can, okay? The problem here to find that j is that I need x equals da-da-da and y equals da-da-da in order for me to do my Jacobian. That's my issue. I don't have x and y equals. I just have u and v equals. So we're going to have to go the long route and actually find out what those would be. Let me go ahead and rewrite these, and then I'm going to start solving for x and y, the slow method. So let's go ahead and solve for x first. I'm going to toss this over. X is equal to u plus 3y. I could take that and plug it in right here. V is equal to 4 times u plus 3y, and then minus y. Distribute your 4. So I got 4u plus 12y minus y. 4u plus 11y. Let's go ahead and solve for y, because that's what we're trying to get here in the end. So move this guy over, and then divide by the 11. And so I actually get v minus 4u all over 11. With this in hand, I can go back and plug this in here. So x is equal to u plus 3 times v minus 4u over 11. It's kind of weird. Distribute your 3 to the numerator, I suppose. And so then we got 3v minus 12u all over 11. You want a common denominator eventually. So this guy right here is going to be 11 over 11. And so those two at the ends combine to make a minus 1u over 11. So there's your x. Okay, so we got our x and our y. Now let's find our Jacobian. Again, that's x sub u, y sub v, x sub v, y sub u. So x in terms of u is going to be a negative 1/11. Y in terms of v is a positive 1/11, minus sign. U in terms of v is a 3 over 11. And y in terms of v is a 1 over 11. I think there should have been a 4 somewhere. No. I'm sorry, it's not in terms of v here, it's in terms of u. Got to use that 4 somewhere, right? So here, 1 over 121 plus, I had 12 over 121. So that would be, what, 11 over 121, which is 1 over 11, I believe. Yeah, 1 over 11. That's what I got for my Jacobian. Okay. Notice that we got a number. It's just numeric. That's good. So could you have done this at the end? Oh, yeah, that would have been fine. But I don't want to rely on that every problem would have that. I don't think that's actually the case. So good practice is to actually do it in the beginning. So let's now go way, way back to what we were doing now. This right here, my double integral of 7 u divided by v now times the 1/11 du dv. Okay, whew. So you could take the 7 and the 11 out. 7 over 11, double integral of u over v du dv. What were the limits that I had for u and v? If you remember and go way back, we had my u was 0 to 1, and my v was 7 to 8. They had almost clearly given that to me, and so I had created that near the beginning of the problem. So let's now integrate my u. Notice it's in the numerator, so I'm going to square it, divide by 2. Go ahead and put my numbers right here. So divide by 2 is going to make a half, and then I got my u squared over v from 0 to 1 dv. Plugging in the 0 is going to cancel, but the 1 will make something happen. The half can come to the front now to make 7 over 22, integral 7 to 8 of basically 1 over v dv. When I integrate that, I actually get ln. That's something we don't see every day. ln of v from 7 to 8. And the way they stylize the answer for them is a little more compact than what we have here. So essentially that's your answer. But and WebAssign should take that. But they have it as 8 over 7 because they use some log rules to make it look pretty. That's fine. It's the same thing. All right, we're done with that section. I did not do all of the questions, obviously. There's a whole lot of other ones, but it's the same process, same procedure. Try them out, and if you got questions, let me know. Thank you very much. Have a great day.